Okay, so we're very happy to have with us today Idan Attias. He's just graduating or graduated from a PhD in Ben Gurion with Professor Kantorovich and Sharon Mansour. And he's about to start in this postdoc in IDEAL, which stands for, I don't know, economics and something and something.
Every topic that is related.
And he will tell us about, well, the junction, as you can see, of information, of optimization, of generalization, of privacy. So it's going to have a lot to cover. Thank you, Dan.
Thanks for the nice introduction. And thanks for coming, because the Europe's deadline is like very soon, so I appreciate that. And so yeah, I will talk about, first of all, it's a joint work with this amazing group of people, and Carolina from Google, Madi, which is a postdoc in Northeastern with Jonathan Movement, Wayne Livni from Tel Aviv University, and Daniel Roy from UFT and University. And this is about stochastic convex optimization. This is the learning model. We want to understand the information theory aspect of generalization in stochastic convex optimization. And as we understand some fundamental trade-off between information and accuracy of predictor, we're going to see some applications to generalization of models in stochastic convex optimization. Maybe the most interesting part to me is the memorization part and differential privacy. Okay. And just feel free to interrupt and engage. It's going to be more fun for all of us. Yeah. So let's start with a motivating question, which is learning and memorization. So when we start the course, I think in ML, probably maybe sometimes the first lecture is about that memorize algorithm does not generalize. Memorization is bad. And the common wisdom is that like learning irrelevant information or actually memorizing will learn generalization. This is the classic ML. And the classic ML also deals with number of parameters that is much smaller than the number of examples. So it's something like that. I don't want to have like polynomial regression that captures irrelevant information. And then modern ML comes with super over-parameterized models. Number of parameters is much larger than number of samples. And somehow we memorize. Sometimes memorization seems even crucial. We generalize, and everything works well.
You will define, I guess, memorization?
Yeah, so there are a bunch of different definitions of memorization. I'm going to precisely define what I mean by memorization here.
These are regression tasks.
Yeah, it's just for the illustration. So what I'm trying to motivate is that we don't understand that very well, the connection between memorization and learning. It seems like lately that memorization is actually a fundamental part of learning. Sometimes you have to memorize. There are a bunch of results about that lately. And we want to understand what is the role of memorization in stochastic convex optimization. And in general, we're going to talk about why SEO is a good model for over-parameterized learning over-parameterized models. Okay, so it's going to be defined formula. It's just a teaser of what's going on. And even more high level, I'm going to present like what we did in this paper. So we wanted to understand generalization in stochastic convex optimization. I'm going to refer to it as SEO. The information theory methods, which you just defined the CMI, conditional mutual information. So I'm going to talk about both input-output mutual information and conditional mutual information. We'll see what it does the trick and actually improve things. So the CMI framework by Thomas Steinke and Zakynthinou. It's a beautiful paper from fall 2020. So we're going to actually show that sometimes good learning algorithms, accurate learning algorithms, must have a lot of information with a training set. Like it's a built-in product, like a property of models. Like if you're good, you have to memorize. I will define what it means, memorization. And then the applications are going to be the CMI framework, while in some models, PAC learning, which I will define soon, is help us obtain like near optimal generalization. In SEO, we're going to see that it's going to help us obtain good generalization, dimension free, but not optimal. So somehow it's like in the middle. It's not as in pack learning, but it's not as bad as other learning algorithms. And optimal learners must memorize even a constant fraction of the data set, which violates a very important property of differential privacy. So that's it. This is like the big introduction. And now we're going to start being more formal. So the outline will be, the results are in SEO, but I want to introduce also pack learning so we can compare results in both models. In general, I'm going to talk about overparameterization, why SEO is a simple model, but is like good enough for I'm starting to understand overparameterization. I'm going to present some generalization techniques that I use, and then I will focus on information-theoretic methods. The first one was introduced by Shu and Reginsky in 2017. It's the mutual information, vanilla mutual information, and then 2020 by Thomas and conditionalmutual information. The main result, the main technical result is like information accuracy tradeoff. Then the applications. I will try to give you slightly like just a proof idea. But I want you to remember that there is a method called fingerprinting method that those of you in privacy probably are familiar with. I think it's a very powerful method that, while technical, the message is super simple. Like if you have an accurate estimator, it must correlate with the samples. Like there is a trade-off. If you're a good estimator, there's going to be correlation and vice versa. Like very simple idea, which is very technical to prove. Yeah. Okay. So the general idea of learning from IID samples. So we have a training set, and it comprises from pairs x and y, drawn IID from unknown distribution. For example, it can be a picture of a dog and a dog. Then what the learning algorithm sees gets to see the sample, output some classifier, a function, a model, and usually chosen from like a predefined function class, hypothesis plus h. And then the goal is to predict an unseen samples. Like if I draw a random point from P, I'm interested in low error. Let's say here is 0, 1. If I predicted 0 and 1, I'm going to suffer either 0 or 1. And the beautiful paper by some guys, Shai Shalem Schwartz, TTI, was in the university. I was in the university. Paul Shamir in Discernible, that was also in the university, and Carl Xena, that then was in TTI. Okay. So this is going to be the model, but first I'm going to introduce a different learning model, pack learning. Are we okay? Okay. So pack learning, the realizable standard case was introduced by Valiant in '84. You got the Turing Award for that, for introducing the formal definition of learning. There is even before Vapnik and Chervonenkis introduced the BC theory, which was formalized to characterize pack learning model later. And then I think Ausler was the first one that formalized diagnostic. There are a bunch of people worked on that, but I think these are the main characters that I'm familiar with the first papers. So what do we have in pack learning? We have an instance space X. Think of that like all dogs and cats in the world. We have an idle space Y, in this case just 0 and 1. There is unknown distribution over the pairs. There is a concept class we want to learn. Then we have a learning algorithm. It gets a training set like n pairs of samples, labeled samples, X and Y, and output a function, H. The error rate is defined as the expected value of the error at random point from D. What does it mean to pack learning concept class? So epsilon delta pack learning concept class. If for any distribution, it's like a worst case definition, like we like in computer science, and some people don't like. So for any distribution with high probability, with probability 1 minus 7, the error of our classifier is going to be competitive with the error of the optimal function in C up to some approximation of C. So probably probably approximately correct. Probably is the 1 minus delta. Approximately is the epsilon. And correct is that we complete with the optimal function of C. If there is a function, optimal function of C, this is 0, and this is the realizable case. Most of the talk is going to be in diagnostic case, so I'm talking about diagnostic model. And this is the main message I want to convey in this slide. ERM is sufficient. Like if you just minimize, you find even an approximate function in C that minimizes the error. In the PAC model, you are guaranteed to have generalization. In the realizable case, is near optimal up to log factors. In diagnostic case, I think is optimal up to constants. And so basically, it's just about optimization. What's the question?
I think they closed the log gap also
Yes,
in.
Steve Aniki closed, but it's not an ERM. It's like an improper
Oh,
error.
right.
2016, Steve Aniki showed like ERM is going to give you VC. There is some log n here. Use log something, 1 over delta, over n. This is the realizable case. In general, ERM cannot remove this factor. And Steve showed how to remove this factor in 2016. And now, recently, there was a best paper in Holt by Kasper Green Larsen that showed that actually bagging is an optimal learner. But these learners must be improper. It was a beautiful paper. Thanks for asking. So, but the point is that ERM cannot do that. In diagnostic case, actually it does. So basically, we don't care if we know how to optimize. We get generalization for free. That's the message in PAC learning. And so let's think about the VC as the number of parameters. So the number of parameters must be sublinear in n for this guy to go to 0. So this is not an overparameterized model. Okay, so ERM is sufficient to get near optimal generalization. And we don't care, in a sense, about it's not true, but we don't care about the algorithm. Like we're gonna guarantee learnability. Okay, this is the PAC set. Second learning model that's going to be our focus is you introduced it very nicely, but I will repeat. So, okay, our goal is to minimize what we call the population error. Let's unpack the details. D is just the unknown distribution. W is some parameters I choose from a subset, a convex subset in RD. And I can assume that it's bounded L2 by a constant. It can be more than like it can be bounded by a general constant like R, but we can normalize, so we can assume that it's just bounded by a constant. The generalization, the population error is defined by F subscript D. Z here is just a latent sample. F is a loss function. So F of W, the parameters of the model, and Z is a loss function that we assume that if we fix Z, it's Lipschitz in W. And it captures many interesting cases in learning, and this is just the notation in SEO. So I wanted to be consistent with the notation in SEO. So yeah, this is the error of an unknown sample. Basically, we chose W. This is the unknown error, like on the test point. So as I said before, we have an axis, the training set, Z1 to Zn, drawn IIT. So F subscript S is the empirical error. So F subscript D is the true error. This is the empirical error. And what we care about is low excess error, similar to the PAC setting. What does it mean? So we have an algorithm that gets a set of n labeled samples. It outputs some a W in RD. We don't it doesn't need to be exactly to output something from W. So if it outputs something from W, it's a constrained optimization. If it outputs something out of W, it's unconstrained. I'm gonna just refer to both of them. But pay attention that it can be like return something that is out of W. And we say that algorithm is an epsilon learner if I given n of epsilon samples, then for any d is going to guarantee that the population error of the algorithm is close to the population error of the optimal function in W up to some epsilon. And here I don't deal with hyperability, I'm just going to talk about expectation. So in the fact model we talk about hyperability, and we talk about expectation. And n of epsilon is called the sample complexity. So an algorithm needs n of epsilon if for any d it can guarantee a small excess. Are we okay with the notation?
Can you go again about what is an epsilon level?
Yes. Here I asked that I could tell you, like, forget about the probability. This can happen in expectation. And also in the SEO model, most of the time I think we can talk about hyperability. In the paper we spoke about hyperability most of the time. Actually, in the CMI framework, the guarantee is not in hyperability. So that's why I'm going to talk only about an expectation. Okay, sample complexity is the object of the minimal size of samples that guarantee learning. Okay, this is the SEO model. Okay, so now I want to explain that the learning landscape, algorithmic learning landscape, is much different than the PACSET. In what sense? The algorithm matter. It's not just minimize. So let's see a bunch of results. First of all, uniform convergence, which basically says the empirical error of any W in the class is close to the true error for a sufficiently large size of sample size. And specifically, the uniform convergence in this model is like roughly square root of d over n. So if d goes to infinity, this guy cannot be arbitrarily small. So maybe we cannot do better, but we can do. So what I like, this is like not a good way to prove generalization in SEO if I want to remove this d. So I need to use a different technique to prove generalization. Maybe somewhat surprisingly, ERM, that's usually thought to be equivalent in the sense to just proving uniform convergence, is actually recently shown that it's not square root of d over n, is d over n slightly better, plus square root of 1 over n. So Vitali-Feldman in 2016 proved the lower bound, and recently Carmon, Dias, and Livni closed the gap in AStats 24 with an upper bound. So yeah, maybe it's slightly surprising that generalization of ERM and like uniform convergence is not exactly the same, but still it's dimension dependent. Okay, so ERM, if I just wanna minimize, I'm gonna add that dimension popping up there. Okay, so gradient descent will have gradient descent, right? So if we're gonna use full batch gradient descent, we take a gradient with respect to the entire training set. Again, it's actually like ERM. This is also recently by Roy. So full batch gradient descent actually is not gonna get us what we want, dimension free bound. But somehow, like simple algorithms and classic algorithms like SGD, stochastic gradient descent, which is like a very simple known proof, gets us like square root of 1 over n. So it doesn't matter. RDD can be like very, very large. Somehow the generalization does not depend on D. So I think SGD was introduced first, as far as I know, by Robbins and Monroe in 51. I'm not sure like they proved this rate. This rate was from the 80s, but I gave them the credit for the algorithm. Another algorithm that actually gets this rate is like not an ERM, but some regularization. This is also by the SEO paper, so it is possible. So the algorithm matters. SGD or regularized ERM, are going to get us like the dimension free bound. So this is like SGD was, I think, we think about it when we take a course like as, okay, this is a cheap way to perform gradient descent. Instead of taking gradient with respect to the entire training sample, we're just going to draw one sample and take the gradient with respect to that. Like the motivation is like, let's save some computation. But actually, it's much more than that. Like it affects the generalizations. There is computation and statistical aspect of SGD, which is maybe surprising. Why this?
But there is here the assumption that no point is used more than once, right? That there's like one epoch in a way. And otherwise things...
One input, yeah. It's not mini batch.
Yeah, no, I know what I mean is that you don't get to the point where you used every point, let's say once, and then you start.
Yeah, so like you draw a fresh sample from the distribution.
Oh, always. Yeah.
True. Like with replacement and without replacement, basically. So the proof works like with when you see every point of it. Okay, so the goal of this slide is to, okay, the algorithm matters in SEO. So it's a simple model, but there is an interesting phenomenon already. As opposed to the top setting where uniform convergence is equivalent to learnability. So hopefully I was able to convince you that SEO model, there is some interesting phenomena of over-parameterization. Okay?
Can you remind me, D is number of parameters or number of size of input?
No, N is the size of the input. D is the predictor. We think about it as the number of parameters. We choose W from capital W, which is a convex subset of I. So we think about D as the number of parameters, and these parameters can be injected to a learning model. So yeah, neural network is not convex, okay? But already, like in the simple setting, I think many results are like just proved like lately. So I think we need to understand the simplest model that already shown the phenomena. And to make the picture even more full, so I took the slide from Ray, which gave you also, I talked about similar topics. So if I think about the regime of the number of parameters is smaller than the number of examples under-parameterized, I will put the pack learning here, and also something that I didn't talk about, the generalized linear models, and where you can learn by using uniform convergence. And there is the deep ocean here, where deep learning is over there, non-convex, we don't know, there are many things we don't know. SEO, but is already in the over-parameterized setting, where the number of parameters is much larger than that. So yeah, I think this is a nice pick. So there are many learning models. We need to understand which one of them gives us what and why.
Actually, can you explain, because some of these are specific models like GLM, pattern is a paradigm. Sure. Like it's not exactly, it's a learning model, it's not a specific model.
So GLM, I think about it also as a paradigm, like where the loss is just a function, is the dependence on the loss of W is linear, like logistic regression. So I think about GLM also as a...
Okay, so you're thinking about the loss part, not the representation.
True. Yeah. Okay, so this was like a background about learning models and why I care about and we care about SEO. So now some background about generalization. So what is the generalization error? Generalization gap is just the difference between the empirical error and the population error of some W. And here I'm taking an expectation. Okay, it's like what you see, like if it's the same, so what you see is what you get. Like if you minimize that and it's close to that, this is uniform convergence. So this is how I define the generalization error. So uniform convergence, again, is a property of the function class, not the algorithm. What you do, but there are a bunch of other techniques that actually analyze the algorithm. So one technique is stability. There are many definitions of stability. Maybe the most strict one is the one when I change one input and I don't want the output of the algorithm to change a lot. This is uniform stability. There are a bunch of other stability. Also, differential privacy is a notion of stability, just the distribution of stability, property of an algorithm. Sample compression, which is a very useful technique with path setting, basically says we can think about SVM. Like maybe I have I don't know, a bunch of points. But in SVM, basically, we can represent this is not something like that. I don't need to keep all these samples. I can just choose the support vectors to represent. Let's say these are the support vectors to represent this function. So I can throw away the samples. So there is I can take the entire sample, keep only a subset, and then this subset can, from this subset I can output a function that is consistent with the entire set. So sample compression basically tells you, okay, you have thousands of samples, give me like 10 of them, such that if I look only on 10 of them, give me a procedure that gives me a function that is consistent with the entire. So most of the information lies in the subset. Support vectors, I think, is the simplest example. And actually, this circumvents uniform convergence. So maybe in binary classification, in path learning, we have uniform convergence, but other settings like multiclass, we don't have uniform convergence. And actually, sample compression is very useful in the path model. But in this talk, we're gonna use information-theoretic approach, which is, like as we said, the generalization is bounded by some information complexity of the output W and S. How much information the output carries about the sample. So just to give you the high level of generalization, let's start with the first candidate by Shu and Revealsabout, 2017. They said, okay, something very natural. The generalization depends on the mutual information of two random variables, the output of the model, and the training sample. Whereas we said before the lecture that the mutual information is just the KL divergence. One way to write it is the KL divergence between the joint distribution of X and Y and the product of the margins. Okay? This is very nice to get a generalization from this object, but does it give us like the optimal rates? So the answer is no.
Yeah, there is a distribution over W for after the algorithm for each sample set. What output the output. What are you thinking of the distribution? Let's see.
So W can be output of random algorithm, and it depends also on a random set.
Yeah.
So there you ask what is the source of randomness?
No. I'm just wondering what the distribution is. The distribution is like a noisy channel where you put the samples and count them output something. This is the distribution.
Not sure I understand the question.
I think I'll say it differently. To measure mutual information, you need a distribution for W. You want to define what the distribution of the W is. I know what the distribution is over samples, but what's the distribution?
So maybe about capital W in this case.
No, so it's like you can think of a distribution over models that is the result of first sampling a data set, then running the algorithm, which might be also random. That is a distribution.
Okay, that's good. I just want to.
So we have a very nice result, but does it give us what we want? So the answer is no. Basili, Moran, Nahum, Shefer, and Yudayev, they show, and also Livni and Moran, they show that for thresholds, the VC dimension, there is a class that the VC dimension is 1, but the input-output mutual information can be unbounded. Maybe it's not surprising for especially experts in information theory. So this is a very nice result, but it doesn't give us even a simple result that we know how to get by different methods. And okay, so maybe let's ask SEO is a different model, and also we showed lately that also in SEO it can grow. The mutual information can be growing with the dimension. So it's a beautiful method, but it doesn't give us optimal rates. Okay, but this was a interesting step along the way. So indeed, as we said, Steinke and Zakynthinou, they introduced a different thing. They tried to normalize, in a sense, the information. Okay, how to think about the CMI. So I have a super sample. It's two NIAD samples from D. I call this one a super sample. Then I draw uniformly a membership vector, which just tells me take the first one or the second one. For each pair, take the first one or the second one. What's been chosen, I call the training sample. What is not chosen, I can refer to as a ghost sample. For those of you from learning theory, it's points that the algorithm didn't see. So think about it as an L2 set, ghost sample, and okay, the algorithm sees the training. So this is just a experimental thought. Like the algorithm don't see this point, you just get to see what's chosen. Any outputs function. And what is the CMI? The CMI now is the information between the output of the algorithm. But with this conditional random variable, it's like the membership vector given the super sample. So a way to think about it is like if an adversary gets to see my output and I give him the super sample, can he recognize which inputs the algorithm saw? I give him 2 ensamples. He should tell me, okay, the algorithm was fed with this one, with this guy, with this guy, and the other guys weren't in the training set. So it's about recognition of inputs from a set of candidates. And also here, the generalization is bounded by this notion of information. And that's great. Like in the back learning, we can get near optimal, like we can bound the CMI by the VC times log n, which is great. Like it gives us near optimal. It fixes the problem for back learning. So it gets us near optimal rates for back setting. But what about SEO? They showed a bunch of other results about like how to bound the CMI, but at least in the back setting, it gives us what we want. Okay, so is this notion clear? Like when I write like that? Okay. So now I'm gonna steal some explanations from Thomas and why to think about such an object. And so the way they thought about it is like normalizing the information that each sample is going to carry only one bit. It's about like distinguish between 2 points. And memorization of a single sample in the input-output mutual information contains unbounded information. But here, if you memorize one sample, then it gives the adversary or the think about the adversary 1 bit of information. So if input-output mutual information is about how well I can reconstruct the input from the output, CMI is a great object for memorization. If I have a set of candidates, how well can I recognize them? How well I can recognize which one of them are the inputs by just observing the output. And this is, I think, the most convincing sentence. The difference between trying to come up with a sketch of a criminal or, okay, I'm going to give you a set of candidates, I'm going to give you a lineup and just pick up one criminal, right? Like this is about recognition. And this is like, okay, I need to sketch actually what I saw. It's harder task, you know.
So anyway, can you explain the rationale? Because in any interesting problem, you have a large mass of samples, which let's call it basic. Like you mentioned cats and dogs, the ones that are really right? And they're actually not that different from each other, so they don't contribute at all, but they make the problem harder. Then you have a lot of samples which are hard, right? Those are the ones making here the decision circles. So giving each sample a bit of information sounds like it doesn't capture the essence of a real problem.
So yeah, we're gonna see that we're gonna we can. So the answer is that maybe the memories, we're not gonna be able to capture these samples that are close to each other. We're gonna be able to, like the algorithm memorize, maybe you're gonna see it in the result. But if two samples are like, if these two guys are very close to each other, we won't be able to differentiate because they gave the similar information to the algorithm. So in this case, we won't be able to differentiate between these two. But when we draw AD pairs, sometimes one of them is going to have a lot of correlation with the output, and one of them won't have a lot of correlation with the output. So the times we can like catch the memorization in the cases where one of the pairs is going to have a lot of correlation with the output, and the other doesn't have a lot of correlation with the output. So the answer, I think, is that sometimes you're right. If these two are very close, okay, I cannot do anything. But I draw them IAD. Sometimes they're going to differentiate, and when I have the output, some of like the proof goes like through a correlation test, and one of them is going to have a lot of correlation and one not, and then we can catch the algorithm and say, okay, you saw this one and not this one. Does it answer?
No, so I understand about the intuition of why learning happens. My question was more about information, because if you're actually given an entire bit for each of those,
yeah,
like in many ways I can remember a lot of bits for free without doing well at your generalization, because I'll just remember all the examples that are near each other, because they're kind of easy to remember.
So you say why the generalization is even correct? That's the question?
Yeah, I'm talking about why the assumption in the next slide. Well, like, maybe I misunderstood and this is just an intuition and not formal, but you're saying I'm going to assume that each example counts for one bit. Is this a formal statement or just if it's an intuition?
It's an intuition. The formal statement is that the generalization is bounded by this object. I just try to explain to give intuition why this guy captures generalization better than the input-output. This is not a formal statement. But I'm happy to chat about it if you have like a...
Let's move on and do it offline.
Okay. So so far it was background. It's not our result. Now we can present our result. So I think the most technical result that most of the applications are going to follow from is CMI accuracy tradeoff. And the informal statement says that if you have a good learning algorithms, sometimes I can design situations where the information must be high. And the point is that the dimension needs to be larger than n squared. Okay. Otherwise, it's not true. If d is smaller than n squared, this is no longer true. So the claim is that if I have a good learning algorithm, you learn something, it needs to have large CMI. And okay, so the formal statement is like, okay, there exists some SEO problem or problems which consist of like the set of parameters that we're going to choose from, Z, the set of inputs, outputs, like samples and labels, loss function, such that for any epsilon learner with epsilon excess error, with sample complexity over epsilon, remember that in SEO the optimal sample complexity is 1 over epsilon squared. For any n that is larger than the sample complexity, and d is large enough, this is before then, there exists distribution such that the CMI is at least 1 over epsilon squared. Okay, we'll see what is the implication of this result. Also, generalization of this theorem is that it holds also for strongly convex loss, where strongly convex just means that any tangent line have a like quadratic lower bound. So yeah, this one, let's say, this one is not strongly convex because here I don't have a quadratic lower bound. But this one is strongly convex because if I have a tangent line, I can have a lower bound that is quadratic. So if there is more curvature, the CMI is only lower one by 1 over epsilon. And also we proved it both of the algorithm output something in W and not in W, constrained and unconstrained. Okay, and the point is that this is also tight, because we can take any epsilon learner, any good learner with optimal sample complexity, and show that its CMI must be bounded by 1 over epsilon squared. So this tightly captures the CMI of algorithms. Okay, so is the statement pretty much clear? Okay, so now let's see the implications.
So just a question of what you're saying. You're putting the exact focus on why uniform convergence doesn't work in CMI. That's the.
I'm trying to understand.
The idea of uniform convergence would be that for any distribution you would have low CMI. What you're saying is that no, you must have.
So okay, I depart from uniform convergence when I understood it's not going to give me dimension-free bounds. So I went to the SEO model. I looked at a bunch of types of generalizations. I know that uniform convergence is not the right technique for proving dimension-free bound. So now I'm going to a new technique, information-theoretic technique, that I know that gives me near optimal rates in other model. And I ask, okay, maybe this CMI framework is going to give me like what SGD gives me and why regularized theorem is going to give me. Can I prove optimal generalization using, so this is just a framework to prove generalization. By analyzing a property of an algorithm, which is like the CMI, the information it carries about the training set. Okay. So we're going to see, spoiler, that indeed it's going to give us dimension-free bound, better than uniform convergence theorem, gradient descent, but it's not going to be optimal. It's going to be 1 over n to the fourth and not 1 over n to the. So this is spoiler. It's going to give us dimension-free, but not optimal. Going to see it next. Does it answer the question? Later. Okay, so a corollary. The sample complexity is 1 over epsilon squared. So I will have an algorithm. I can have an algorithm with optimal sample complexity, but the generalization error from CMI is going to show me that it doesn't converge. Meaning this object is not going to show me that it goes to 0, while I know that it goes to 0 by other technique. How can you see that? So you can just plug in CMI here to be 1 over epsilon squared. And now if I take n to be 1 over epsilon squared, this guy is not going to 0. So we wanted to understand the power of CMI in SEO. And this result shows us it's not going to be optimal. For any epsilon learner, it was shown previously that is true for gradient descent. So we know that for gradient descent, CMI is not going to give us the right generalization. Here we show it doesn't matter. If you have a good algorithm, the CMI is not going to work. It's not a property of gradient descent. It's just if you have an accurate learner, there's going to be a lot of information. And we can show that that actually the rate is 1 over, like it's somewhere in between. It's not 1 over square root of n or 1 over epsilon squared, but it doesn't have dimension. So it's good, but not optimal. So this is the first corollary of the result. I promised to talk about memorization, so let's talk about memorization. Second application. So memorization that is going to be formalized by something I call membership inference attack or tracing attack, known in the differential privacy literature. Tracing is like the leakage of information of the training set. Like I see the output of a classifier, and then I can realize, okay, my information was in the training set, This is a situation we want to avoid. So yeah, we have a training set, Z1 to Zn. Now what we do, we sample a fresh data point, let's say a cost sample, independent of Zi and the output of the model. I'll call it ZIP. Z1I is the true sample, and Z0I is the sample that the algorithm didn't see. Now I'm going to flip a fair coin, BI. I'm going to give it to the adversary. I'm going to show you Z BII, one of them. I'm going to show you one of them. Uniformly is going to be chosen. The adversary sees only the output of the algorithm. It doesn't need to know the algorithm. It's a black box idea. He sees the output. He sees one of them uniformly. And here I say it needs to know the distribution. This is not actually true. It needs to know only the approximation of the expected value. But let's say it knows the distribution. And the adversary, based on this information, should output a bit. And it's correct if the bit, if it says if PI was in the training set or wasn't in the training set. So there are two samples. I give him one of them uniformly. He needs to tell me, okay, you saw this sample or you didn't? This is the game. Very motivated by the CMI, as you can see. Okay, so this is is it clear, the memorization? What do you call the memorization? And what's how we quantify what is a good adversary? So there are two benchmarks. We say the adversary is alpha sound. If the adversary doesn't blame innocent points, like if there exists some I, so we're going to play for each sample. If there exists some I where the adversary is going to see the ghost sample and he's going to say, no, this was with the sample, this is a bad event. So I want this bad event to be smaller than alpha. This means that the adversary is alpha sound. And we say that the adversary captures like m samples from n or certifies a recall of m samples if he captures like m points that were actually in the sample. So if I sum over all z1i where zi was in the sample, and the adversary actually says yes, so it captures m of this with some constant number, then I say that it captures m samples. I'm going to maybe explain later where these guys are playing a role in the result. Okay, so let's see if the picture is clear. What's the game, and how I quantify what's a good adversary, if it succeeded or not. Where we need to, the adversary needs to know the output, black box. He just gets to see one of them, and he needs to know an approximation of the expected value and not actually see.
This game sounds similar to the game of differential privacy, except you take, it's the worst case, but you take like the average.
Great. So for sure, yeah. If we can do that, means like we can violate privacy with more relaxed notion. Like if the adversary can do that, it's actually worse for differential privacy in a sense. Differential privacy says every neighbor data sets. Here I'm just telling you, okay, a fresh random point from a same distribution, and I can still know which one was in the sample or not. So definitely, I'm gonna explain it later. And we have a formal proof that actually this is a stronger notion of violation of privacy. We're gonna write it roughly in the paper. It's gonna be probably future paper. But indeed, it's like a relaxed notion. Like if I can do that, it's much worse for privacy. Okay. So this is and what's the message? The message is that optimal errors sometimes, not always, sometimes we can show that they memorize constant fraction of the data set, which is a very strong statement. Informally, there exists a universal strategy for the adversary, such that if I give him an instance of SEO, if the adversary is doing okay in terms of accuracy, small excess error, it comes with the cost of disclosure of memberships in the sample. And this is the importance is that the dimension should be large enough. It's a phenomenon of large dimension. So this is, I think, easier to read. This is like a bit more messy. So for any epsilon, every alpha is the soundness parameter of the adversary. There exists a SEO problem, an efficient adversary, such that for any epsilon and every epsilon learner, if the number of samples is larger than some complexity, and again, d is larger than n squared, log n over alpha, that's where the soundness parameter plays a role. So we can find distributions such that efficient adversary can be alpha sound and certifies 1 over epsilon squared examples. So alpha sound is like how reliable is the algorithm when it claims points and certifies a sample. Here is m, here is 1 over epsilon squared, where the constant you saw in the previous definition hides here. If I ask for a larger constant, I can certify less samples, but it plays a role just here in the constant. And again, for strongly convex, we can do it for 1 over epsilon. Okay, so the message is, if you have an accurate learner, I can come up with a very simple adversary, so just test correlations, and it can capture a lot of samples. Okay, so I prepared this slide. This is we didn't think about it at the beginning, but then we talked with some people from privacy, and this is a new result to them. So what is differential privacy? Specifically here in SEO is that we say that randomized algorithms epsilon delta differentially private if you give them two neighbor data sets that differ only in one data point, and for all events that are like in the output of A, then basically the distribution is going to be similar on S and A, S prime. Okay, so one point doesn't change much, the distribution of the algorithm, the output distribution of the algorithm. Okay. So a beautiful paper by Vasily Feldman, Wall, and they showed that the optimal rate in differential length. This is another. We're asking more for the algorithm, not just be accurate, also be private. So they showed that this is the right rate. It's like 1 square root 1 over n, and then here I have square root of d. Here is like some privacy parameter. Think about it as a constant over n. And what we can see that they showed already that if d is larger than n squared, this is not going to go to 0. So it's known that if d is larger than n squared, there is no differential price. What we showed that actually if d is larger than n squared log n, it's a much stronger claim. There is a universal attacker that again identify membership of a constant fraction of the data set. So both the points are drawn IIDs, not just like I don't have the freedom to choose any point in the neighboring data sets. I also can identify a constant fraction, identify many points. And then so we wanted like to see, like we're thinking, probably it appears in like already in the differential privacy literature. And indeed, there are like 2 beautiful papers that showed something similar. But the thing is that they worked in L infinity or L1, and the result does not follow. We cannot deduce our result from this. I think in some sense our result is much stronger. We're going to formalize it. So we talked to them and they were like, okay, this is indeed true. This is new for the differential privacy. And yeah, here in a pictorial way, where they showed like 2019 paper showed that here there is no differential privacy. We showed this regime. It's not just that you don't have differential privacy, it's much worse. Like the cost of not having a differentially private algorithm means that you're gonna expose a large fraction of the data set. So I find this conclusion very interesting, and we'll keep exploring this this direction. I have 4 minutes, so I don't know if it's a good idea to show the construction. I'm just I wanna just highlight what's the main tool. The main tool is the fingerprinting lemma that very roughly says that high accuracy output comes at the cost of large correlation to the training points, meaning we can find situations where it happens. And this helped us to create a situation where there is a distribution such that the sum of correlations of training points and outputs is large, while if I draw a random point, the correlation is small. Okay. So I can create a situation where the sum of correlations is high. If I draw a random point, the correlation is small, then I can do correlation detection between pairs. This is very roughly, like the last 3 minutes, I don't think it's a good idea to go so deep. So last slide. Takeaways. We need to think about, I think, these things. Sometimes, to have accurate learners, we need to take into consideration that if the dimension is large, there's going to be large information about the training set. I think this is an important concept to understand, and the price of that. And then it means that in the sense I explained, this is a memorization. And the adversary is not even like a very, like it's just the correlation test. The price is the membership of many samples may leak, and this is interesting, I think, like differential privacy. The CMI framework, while it's beautiful and like gives us optimal rates in path learning, in SEO it's like dimension-free rates. It gives us dimension-free rates, but not optimal rates. And that's for future work. Maybe there is a simple information measure which gives us optimal rates in SEO. And this is, I think many people are working on that. Information attacks on large models and data reconstruction. If I want to reconstruct, probably I'm going to focus on input-output mutual information. But I think like there is a room for research here. I think many researchers are working on that nowadays. And basically that's it. I don't have another slide.
So where the first bullet, I lost track with all the equations. What theorem does this bullet come from? Either theorems? The learning algorithms must obtain a large amount of information.
It's the one with the CMI. Yeah, this one. If I have forget about all these words. If I have an epsilon learner, then in high dimension the CMI is large. So if you give me an epsilon learner and the dimension is high enough, and I look at the sample and the gold samples, I can like blame you for like you use this one and not this one. And I look at a bunch of things. And this is like inherent in the problem.